sorry we don't get to meet in person. This is going to be a lot less good. I think these lectures this way are very boring. I hope that won't be too bad. Maybe I can tell more jokes or something. We have not too much more material to go and we'll be finished though. We were running a little ahead until this happened, so I hope we can still finish. I'm going to do today's lecture using some of Paul's Online's math notes. You can Google Paul's Online Math Notes, look at Calculus 3. They do a 3-semester calculus course, and line integrals, the last part of it, is what I'm going to do this out of. We'll just do this on the board, and then I'll do some things out of the book here too, and assign some homework problems out of the book. These lectures will be done basically at double speed because of the electronic constraints, but you can go back and rewind and get the information back as you need it. So here we go. Here's the line integral that we were doing last time. We can evaluate a line integral f of x, y, ds, which is basically taking the area under a curve as we move along, under a function as we move along a curve in the xy plane, we said, right? It's like the area of a curtain is one interpretation of it. By evaluating this, f at x of t, y of t, or x equals h of t, y equals g of t in this presentation. X of t, y of t, square root of dx dt squared plus dy dt squared dt, that gives you the area of the curtain that's below a surface and over a curve in the xy plane. Something like this we can draw here. You have a curve you're traveling along C in the xy plane. We're underneath a surface up here, and on the curve, or over the curve on the surface, we get this kind of an image, and the line integral calculates the area of this curtain here. And this was the formula we had to evaluate it, right? We have an evaluation formula going with every definition. So one of the nice things about these notes here is you can click on things and get the get some examples. This square root dx dt squared plus dy dt squared can also be written as the length of r prime, right? This is r prime's length. And so we have the line integral can be written in short as f of x of t, y of t, length of r prime of t dt, along a parametric curve, c equals x of t, y of t. And here's an example. Let me erase my marks here. Suppose we want to evaluate the line integral of x y to the fourth ds along the curve that's the circle, x squared plus y squared equals 16. All right, we did a little bit of this last time, and I hope this isn't too much review. How do we do this? Just click on here and you can see to parameterize a curve, a circle of radius 4, where you can use x equals 4 cosine t, y equals 4 sine t. Then if you want to go around the half circle, this one says, let's just do it around the right half of the circle. We'll let t, which is the polar angle, when you do this parametric representation, goes from minus 90 degrees to plus 90 degrees in the xy plane. And so we're sweeping out the curve. Oops. Right here. Moving this way from an angle minus pi over 2 to plus pi over 2. Here's C. As we move along that curve C, we want to find essentially the area of the curtain, whose height is x times y to the fourth, sitting over the xy plane. And so we compute dx dt and dy dt. Those are the derivatives are minus 4 sine t, 4 cosine t. And then r prime is the square root of dx dt squared plus dy dt squared is square root of 16 sine squared plus cosine squared. Well, sine squared plus cosine squared is 1, so the square root of 16 is 4 dt. It's written here that ds is length of r prime of t dt, back in the presentation up here, so the ds is this part here. Now, we write x and y as a function of t in the integral. X is 4 cosine t, y is 4 sine t, and I've got a fourth power of y. replace ds with length of r prime of t4 dt. When we do that integral, right, this one you can do, since cosine is an odd power, remember this from calculus 2, you can substitute u equals sine, and this becomes u to the fourth, and cosine t dt is du. So we have integral of u to the fourth du is u to the fifth, where u is sine t, and this integrates then to 8,192 over 5. There's the evaluation of a line integral. Hopefully that looks familiar. Now let's go back. Today we mostly want to look at line integrals part 2. And this says oops, what's the next one? Line integrals over vector fields. Here we go. There's another kind of line integral. The line integral we did was this kind. Scalar line integral is sometimes called. F of x, y, ds along a curve C. That could be evaluated. This isn't the definition. The definition was a limit of a sum, but you could evaluate it by taking the integral over the range that your parametric curve went, t going from a to b. F of x of t, y of t are the coordinates along the parametric curve. Length of r prime of t dt. That's how you could evaluate the scalar line integral. How shall we define this vector line integral? What turns out to be useful is to define the integral of f dot dr, that's its notation, as the integral of f dot r prime dt. So the vector line integral will be the integral denoted integral f dot dr along the curve C. And what that notation means is this. It's the integral t going from a to b, the values of t as you run over the curve C parametrically, f of r of t, that's the path function, that's the curve, C is given parametrically by rt, times r prime of t dt. Another way of saying this is that this is defined to be integral of f dot the unit tangent vector ds. So you can define the vector line integral as the scalar line integral of f, function of position, dot the unit tangent vector to the curve. So sometimes see it written that way, it means the same thing. But you can define the line integral along a curve C of, that's the vector line integral, as f dot the unit tangent vector ds. That's the line integral of f. But then ds is r prime of t dt, length of r prime. And f is dotted with the tangent vector, which is r prime over length of r prime. These cancel, and what you get is that this definition of the vector line integral is f dot the unit tangent vector ds can be evaluated as f dot r prime dt. So on the online math notes, they just give that representation. But sometimes you'll see the other one. So I just wanted you to be familiar with it. Alright, so two types of line integrals, the scalar line integral, which is the one we just did an example of, and the vector line integral, which is defined in terms of the scalar line integral, can be evaluated this way, f dot r prime dt. last section. Very good. Alright, so here's an example. Suppose we want to evaluate the vector line integral. By the way, what good is this? If you take a physics or engineering course, you'll find that this is precisely the way work is defined along a curved path in multiple dimension space. Its integral F dot dr is the work done by a variable force along a curved path. That's a generalization of the previous work concepts that you got earlier in the text. So work is defined this way. Suppose where F is a force, suppose F is 8x squared yz I plus 5zj minus 4xyk, and C is this curve given this way. Ti, t squared j, t cubed k for t running between 0 and 1. How do we find the integral F dot dr, the work done by this force along this path? Well, we said we can write F along the path by writing the path parametrically. So F of r of t is F of, you put in t for x, t squared for y, and t cubed for j in this formula. So you get 8 times t squared times z is t cubed, right? I, and so forth. You, for 5z, you plug in 5t cubed, and so on. So this gives the force as a function of t along the path in three-dimensional space. And then r prime, if you go back and look at the initial path, we just take the derivative term by term. 1, 2t, 3t squared is r prime. Now you can compute F dot r prime, right? Take this times this, plus this times this, plus this times this, just the usual dot product. And here's F dot r prime. The line integral is very easy. You just integrate F dot r prime, t going from 0 to 1. And you get this result. 1 unit of work done along the path. How about that? Here's another one. Suppose we have a force that's xzi minus yzk, and c is a line segment from minus 1, 2, 0 to 3, 0, 1. How do I do that? Well, you write parametric equations for the line segment, and then you take the derivative of that, r prime, compute F dot r prime, and integrate it, just like in the last example. So here it is. To parameterize the path, you can say that the position is 1 minus t times the one point plus t times the other. We said before that you could write this as the coordinates for p, the first point. This is the way we did it. The coordinates for this first point minus 1, 2, 0, plus t times the difference between those. 3 minus a minus 1, 0 minus 2, 1 minus 0 is the other way to do this. So take the first point plus t times the second point, and let t times the difference between the points, and that will run when t equals 0, you get the first point. When t equals 1, you get first point plus second minus the first, you get the second point. And so this one is, you just wrote it this way. So here's the parametric path for the line segment. Now I take the force, which was xzi minus yzk, and put in 4t minus 1 for x. So here's x, put in t for z, x, z, I, minus yzk, and get this is the force vector along the path at any value of t. Once we have r, we can compute r prime just by taking the derivative component by component. 4 minus 2, 1 by taking the derivative. Then F dot r prime is this one, just this times this, plus 0 times this, plus this times this. F dot r prime, and then you just integrate F dot r prime, t going from 0 to 1 as beginning and ending points. You get 3 for this integral. So there's how to evaluate vector line integral, integral f dot dr. What this means geometrically, I think it's always nice to know why you're doing this. I told you it's the generalization of work. If you have a path C, we used to say work is force dot displacement. Remember that earlier in the text? So if you're running through a vector field, here's a force field in the plane, F. At any point along the curve, you've got r prime, remember, is the tangent vector to the curve. So if I take f dot r prime, what do I get? F dot r prime is the component of force. If I take f dot r prime over its length, I guess I should say. This is a unit vector that's tangent to this. This gives you the component of force in the direction along the path, and what you're doing is you're integrating, saying the work is integral f dot dr along the path, but integral f dot dr is defined to be f dot t ds. F dot t is this here, the component of work in the direction along the path. So you're integrating how much force is pushing you along the path as you move. That's what the line integral is, and then the notation for this is to write integral f dot dr. But computing this line integral as we just did is computing the component of work pointing in the direction tangent to the path. It's getting work along a curved path by a variable force. That's what all this is about, being able to evaluate that kind of thing. This is actually used in lots of fields. Fluid mechanics also uses this. Well, if you write dr dt, if you write dr, oops, as, let's say if we write f as p, q, r, having those components, and we write dr as dr dt dt, well, this is dx dt, dy dt, dz dt, dt. So here's f dot dr dt dt. This will be interpreted as dr dt dt. That's the way we said we can evaluate it. Then any line integral can also be written as p dx dt dt. Plus q dy dt dt plus r dz dt dt, where dx dt dt we call dx and so forth. And so we can rewrite this other notation for the same thing. When you see this notation, integral p dx plus q dy plus r dz, it actually is just another notation for the same line integral we already have. So there's at least three ways to write a line integral that mean, a vector line integral that mean the same thing. This is one of the confusing things about this section. When you see integral f dot dr, that means the same as integral f dot t ds, means the same thing as f dot dr dt dt, means the same thing as integral p dx plus q dy plus r dz. These will all be just different notations for the same thing. The vector line integral.